everyone. My name is Omar Delarosa. I'm going to be talking about mixed initiative level design with RL Brush. I'm representing several co-authors listed here, and we more or less are all from New York University, where I am located at the moment as well, New York. So to start kind of with the motivation behind this, we started kind of with like these three questions in mind, like could humans and AI design game content together? And if they did, would the results improve on each one working alone? And does leveraging small data, which I'll explain, does leveraging small data improve creative workflows of humans? And this is the idea that models that we put inside of a user interface, a level editor, small client, could they improve the day-to-day workflow? So I'm going to start by describing what PCGRL is. And the idea is that it combines a couple of concepts. The first one is procedural content generation. So this is the name given to when game content, such as levels or quests or objects, game content is generated algorithmically. And there's a couple of famous examples right now. I've listed two, No Man's Sky and Spelunky, but this actually goes way back to maybe the 80s or the 70s. Very simple games at times when resources were very limited on computers. Could leverage procedural content generation to save memory. The game Elite, I think, is one of the most famous examples that had a space content, planets, and whatnot. Anyway, the other part of PCGRL, it was basically reinforcement learning. And this notion of reinforcement learning takes a way to model game playing as a, well, among other things, but in terms of game agents, as a particular type of machine learning, and the systems are agents taking actions inside of an environment with the goal of maximizing rewards. And this is a subset of these kinds of unsupervised or minimally supervised machine learning concepts. And they exemplify a solution to the problem of, say, not having a lot of hand-labeled data. So take cases in which you might have a lot of images that are manually classified as cats. This is the type of machine learning that benefits when such labeling is not available by human experts, let's say. You could actually have the agents play the game themselves for a while and then generate the data set. So PCGRL really combines these two things. And what it aims to do is to essentially take the act of content creation and treat it like a Markov decision process, meaning it's a sequential task. There's more on the original paper, which I've put the link to in the slides, but the environments themselves can now be sort of swapped. So instead of having a game playing agent, you actually have a game environment tile map generating agent. So you have game levels, you have tile maps in the case of 2D games. The action space then is whether or not to place a tile or to place a game object. And the agent is essentially using, it comes in a couple of different flavors, again, described more in depth in the paper, in the original paper. But there's a narrow agent, a turtle agent, and a wide. You could think of them as just different strategies in which it operates on the map and different sets of features that are fed into the model. And the reward function here is based on level complexity and maximizing the solution path length. Because it's using an example, like it's game agnostic, this can actually vary by game. But in the case of Sokoban, which is the one I'll be showing, that this is simply based on an A-star solver type of approach to determining how long did it take the A-star solver to solve the resulting level. So I'll introduce RL Brush, which is the tool that is available for demo on the web right now as well. And what we did with it is to embed the models that have been pre-trained using the PCGRL algorithm and put them at the top of the user interface. And this makes them available as essentially real-time real-time suggestions. We're calling ghost suggestions. The user can then click on them and then apply them to their map in progress. So the full user interface looks like this, and you can switch between different skins like a dungeon or a classic Sokoban tileset. The user has several options there as well. And you can think of these as the model hyperparameters, and they really allow the user to determine two very important aspects that will control the quality of the output. So steps essentially manage how many recursive calls of the sequential model will be invoked on themselves after the user's input is fed in. And this can improve the quality of the suggestion. So if you say have 7 steps, the model will recurse 7 times before showing the suggestion to the user. And this is all sub millisecond scale, so it's imperceptible. The radius is essentially how much of the current map the agents will receive. You could think of it as a von Neumann neighborhood, and the last tile the user clicked on becomes the center, and there's some configurable radius around that center that will be considered by the model. The code is on GitHub, and as I mentioned, rlbrush.app. You can go to it now and play around with it. I don't have a simple way to open it from these slides, but you can do it on your own time. The tileset switching and play mode is all supported in the user interface. So you could just use it as a Sokoban game or a tile map editor. You don't have to use the AI. But the overall architecture of the system is simply embedded TensorFlow models inside of our user interface. And they use TensorFlow JS to take the Python safe models and put them in. There's an additional 4th agent. It's called majority agent, but this is a simple 2/3 ensembling of the other agents. You could think of it as a meta agent, which is how we refer to it in the paper. We also, through the process of developing this, did a small user study by sharing the web app on social channels. And we essentially defined level complexity as the number of moves required by an A-star solver, and invalid levels to be any level that can't be solved by an A-star solver. These are some examples on the right. The user study allowed users to basically go through a whole workflow, and you can see 6 steps here of how a user might make a level. And then the final one is, or actually you could say steps 1 through 6 are clicks on models. And then the final 7th step at the bottom is the human making a correction to say improve the level quality. We found that users that clicked on an AI suggestion at least once generally made levels of higher complexity than those that didn't interact with the AI at all. The majority agent was also the most popular. This is the ensembling of the other results. And this could be because it simply actually gets the best of all worlds. So it has a little bit of a bias toward picking the best just by its design. But for the most part, that's where we're at. We're hoping to add other games in the future. The models are trained on Zelda, and it is a relatively game agnostic framework.